So what exactly is DITA, and who's behind it?
DITA is a universal robot visual language action model, jointly released by 7 institutions, including the Shanghai AI Laboratory and Zhejiang University. It's a diffusion transformer-based strategy that can adapt to new tasks with just 10 fine-tuning steps. Essentially, the robot only needs to watch 10 times. It has only 334 million parameters, making it extremely lightweight, and it requires just a single ordinary RGB camera, which dramatically lowers the hardware barrier.
That's fascinating. But why do current VLA models struggle with new environments?
Great question. Current VLA models show potential with massive data, but they often fail in unfamiliar settings. The root cause is their reliance on external action heads to predict actions, which forces a compression of the deep link between visual features and actions. This leads to information fragmentation and shallow fusion, limiting adaptability. When encountering new tasks, accuracy drops significantly. It's an architectural bottleneck, hindering generalization in open worlds.
So how does DITA overcome that bottleneck?
DITA achieves lightweight deployment with only 334 million parameters, breaking the need for high computing power hardware. Its few-shot learning lets robots adapt to complex real-world environments with just 10 human demonstrations. Plus, it uses one ordinary RGB camera, no expensive sensors required. In simulation benchmarks, it achieves industry-leading performance, proving a minimalist architecture can deliver dominant results.
How does DITA handle actions differently from mainstream models?
Mainstream models rely on external action components. Discrete action architectures segment continuous spaces, causing precision loss, and external diffusion heads have shallow fusion with the backbone network, underutilizing visual features. DITA uses a causal transformer for endogenous denoising, placing visual and action tokens in the same context window for attention interaction. This directly denoises continuous action sequences within the network, avoiding information bottlenecks and achieving precise pixel-level targeting.
What's the core principle behind this design?
It's called in-context conditioning. Visual and action tokens share the same causal context, so action trajectories during denoising interact directly with original image patches. This breaks the architectural bottleneck of shallow fusion, giving the model pixel-level spatial sensitivity. It can capture subtle changes in ambient light and perceive tiny action offsets. This fine-grained alignment is key to the performance leap.
How does DITA process data to achieve that?
Data processing starts with multimodal tokenization. Human language instructions are encoded into semantic tokens via the CLIP model, and third-person camera images have patch features extracted by Dynov2. Both paths converge into a Q-former plus film module, which filters out background clutter based on language instructions, extracting only core visual features related to the task. This reduces computational load and provides efficient input for fine-grained alignment.
So how does DITA actually unify different robot actions into one system?
Great question. DITA's diffusion model unifies actions into a 7-dimensional continuous vector. This includes 3D translation, 3D rotation, and gripper status. It's perfectly aligned with image and language dimensions through zero padding. During training, we inject Gaussian noise into real actions, and the model learns to predict and reverse that noise. At inference time, language instructions and images are concatenated with pure noise, and the model progressively removes noise over n steps to output smooth, reliable execution commands.
That's fascinating. How does DITA learn from so many different robots at scale?
DITA undergoes large-scale pre-training on the cross-embodiment dataset OX, which contains operational experience from many different robots. The model fully absorbs general operational intuitions from this heterogeneous data. This validates the perfect combination of diffusion architecture and transformer scaling laws. It can process data from different perspectives, tasks, and action spaces, ultimately condensing into a universal policy brain with strong physical robustness.
So does that pre-training help it adapt to new environments quickly?
Absolutely. It provides a dimensionality reduction level of prior knowledge for downstream real-world tasks, allowing the model to quickly transfer to new environments and reduce fine-tuning costs. In multiple latest simulation benchmarks, DITA comprehensively outperforms mainstream models. Radar charts show all key dimensions at the outermost ring.
Which other models did you compare against?
The four other main baseline models include OpenVLA and Octo. Tests cover various spatial targets and long-sequence subtasks in Libero, as well as complex 3D environments like Simpler, Maniscale, and Calvin. This comprehensive advantage proves the effectiveness and generality of the architecture design. DITA successfully breaks through the performance ceiling of traditional methods.
Can you give me some specific numbers from the simple environment benchmarks?
Sure. For the Koken matching task, DITA achieves a complete success rate of 83.7%, rising to 85.5% in variant environments. The open-source visual language model gets only 54.5%, and the Octo model just 0.7%. For close matching tasks, DITA succeeds at 76%, still 73% in variant scenarios, surpassing RT1. Its in-context learning capability helps it handle variations naturally.
What about the Libero benchmark results?
In Libero, DITA's average success rate is 82.4%, leading OpenVLA by about 6 percentage points. In long-sequence tasks, DITA achieves 63.8% success. With a wrist camera, it rises to 83.6%, outperforming competitors by over 14%. Tasks include spatial, object, goal, and long sequences. Long sequences are the hardest, and DITA achieves a significant breakthrough there.
That's impressive. How does DITA perform in the Calvin Blind Challenge?
The Calvin evaluation is a strict blind challenge. The model is trained on ABC and tested in unfamiliar environments. Perception relies solely on a single static RGB image, with no additional game detection information allowed. DITA scores 3.61, while the unpre-trained version scores 2.38. This demonstrates extremely strong knowledge transferability. Migrating from massive real-world pre-training to unfamiliar platforms, efficiently executing continuous actions under extreme perception limits.
And what about complex 3D environments like Maniscale?
In Maniscale, DITA shows overwhelming advantages. In single-object complex 3D rotation grasping tasks, compared to the EDF traditional diffusion head model, DITA's success rate leads by an absolute margin of up to 20 percentage points. In extremely cluttered stacking scenarios with severe occlusion and objects piled on each other, DITA's success rate still leads competitors by 12 percentage points. This benefits from its in-context conditioning fine-grained alignment mechanism, which achieves deep binding between visual pixels and action trajectories, proving DITA's architecture has extremely strong spatial adaptability and visual robustness.
So you're saying that dominating virtual simulations is just the beginning. What comes next?
That's right. Fixed lighting and position offsets, along with ubiquitous distractors, pose new challenges for the model. The sim-to-real gap is a key obstacle for robot deployment. DITA needs to verify its general operational capability in real physical labs. Can it handle complex realities with only a minimal number of human demonstrations? This is a necessary test from theory to practice. Subsequent experiments will reveal its true robustness and generalization boundaries.
How did you set up the hardware for real-world deployment? Did you use expensive equipment?
Not at all. DITA's real-world deployment uses minimalist hardware. The execution end uses a 7-DOF arm with a robotic 85 gripper to ensure basic operation. The perception side uses only a single third-person view RealSense D435i camera, completely abandoning expensive multi-camera arrays or wrist cameras. The computing base is a single NVIDIA, a 100 GPU, stably controlling the entire process at 3 Hz. This low-cost solution greatly lowers the real-world deployment barrier.
That's fascinating. How many demonstrations does the model need to adapt to a new environment?
Facing a new environment, the model needs only 10 human demonstrations, using low-rank adaptation for fine-tuning. The rapid motion adaptation differences are handled. The entire fine-tuning process requires only 20,000 steps to master new skills, completely bridging the gap between different robotic arms and physical environments. In 2 real-world tasks, it achieves a 63.8% success rate, significantly and comprehensively leading similar mainstream robotic models. The minimal sample requirement greatly reduces the real-world deployment barrier, proving the strong transferability of the diffusion transformer architecture.
Can you give me an example of a long-sequence task DITA handled well?
Great question. In long-sequence real-world tests, DITA excellently completes placing a bowl and closing the drawer. Competitor OpenVLA, after the first step, immediately loses memory and completely mistakes the bowl's insertion position and subsequent step order. DITA accurately executes all 4 steps. This multi-step long-sequence logical dependency is extremely challenging. Most competitors lose context in long-sequence tasks. DITA demonstrates remarkable coherence and spatial reasoning.
What about environmental variations, like different backgrounds or lighting?
Facing background variations, like a table replaced with a heavily patterned new environment, DITA still accurately locks onto the racket. Under extreme lighting changes, dim or bright light causing severe surface reflections, the model's action output remains smooth and aligned, unaffected by visual interference. When a large number of disordered clutter objects are suddenly added to the table, the model is not misled and directly targets the teapot and left cup. These tests prove DITA's strong robustness to various environmental changes. Its deep visual action binding remains reliable under real-world interference.
How does DITA compare to competitors on tasks involving spatial reasoning, like grasping?
Competitors often misidentify grasp points, like grabbing the cup's edge or the teapot spout instead of the correct handle. Facing extreme 3D rotation tasks like lifting and pouring, competitors often freeze mid-air. These failures expose the fundamental limitations of external action heads in spatial understanding. DITA, with in-context conditioning, deeply binds original visual pixels with action trajectories, giving it a profound understanding of 3D spatial relationships and fine-grained features. DITA perfectly overcomes the competitor's fatal dead spots with smooth, non-stuttering actions. This comparison fully proves the overwhelming advantage of the endogenous denoising architecture in complex operations.
You mentioned DITA defines a new paradigm for universal VLA strategies. What makes it so revolutionary compared to existing approaches?
Great question. The key architectural revolution is that DITA validates the superiority of transformer endogenous denoising. It completely abandons the rigid external patch design approach that previous models relied on. This is a fundamental shift in how we think about vision language action models.
That's fascinating. How does it handle data scaling and learning across different robots?
For the first time, the data chain successfully runs the scaling law in the robot action domain. Massive cross-embodiment data is perfectly integrated and transformed into universal physical knowledge. This means the model can learn from diverse robot platforms and generalize that knowledge effectively.
So what does this mean for practical deployment? Is it expensive to set up?
Not at all. Low-cost deployment is a core feature. It relies on minimal parameters, just 334 million, and a single ordinary camera. You only need 10 fine-tuning steps to complete complex long-sequence tasks. This provides a reproducible, lightweight baseline for universal robot policies that anyone can use.
That sounds incredibly accessible. Is the model actually open source?
Absolutely. DITA offers a fully open-source baseline model to the global embodied intelligence community. The model is extremely clean and lightweight, making it easy for researchers to reproduce and improve upon. The open-source ecosystem completely paves the way for efficient learning of universal robot policies.
How does this lower the barrier for new researchers?
The ultimate minimalist design lowers the entry barrier and accelerates technological iteration. Researchers can quickly develop new skills based on this model without needing massive computational resources. A fully open ecosystem is expected to accelerate the puji of intelligent robots in real life, laying a solid foundation for subsequent large-scale collaborative innovation.
Who's behind this project? It sounds like a major collaborative effort.
Yes. The DITA paper is officially released and completed by 7 top institutions. The research team includes the Shanghai AI Laboratory, Zhejiang University, and the Chinese University of Hong Kong. The project is supported by the National Key R&D program, which reflects its strategic significance.
And how does it actually perform in benchmarks compared to larger models?
This work validates the scalability of diffusion, transformers in the robotics field. With only 334 million parameters, it can surpass larger models in complex long-sequence tasks. That's a remarkable efficiency gain.
So what's next for DITA? Where can researchers find the resources?
The open-source baseline model lowers the research barrier for universal robot policies. Future attention can be paid to DITA's application and expansion in more real-world scenarios. Code and model weights are publicly available on the project homepage for community reproduction. The path to universal embodied intelligence may become clearer in the future